Hello everyone, welcome to another video from concept to circuit. In this video, we are going to implement a full FM transmitter and receiver using ADALM Pluto. For this implementation, we are going to use two ADALM Pluto, one working as a transmitter and one working as a receiver. In the previous video, we implemented a FM receiver and we tuned it into a local station. Now we are going to make the transmitter as well. So what we are going to do is I have downloaded an audio file. We will process the audio file and do the required upsampling and also uh, uh, FM modulation and then transmit it. And in the receiver, we do the demodulation and play it back. In this way, we can see how is the quality of the received signal and how well is FM uh, transmitter and receiver are working. And to make it, because we are going to go and look at other modulations as well in the future. What we are interested as well is to see how uh, how transmitting in higher frequency ranges will affect our performance. That's why for this code, we are going to transmit and receive at a high frequency 5.8 gigahertz. Okay, so yeah, I talked about the modulation and then demodulation, but I'm going to go over the math once again to uh, we talked about the demodulation before, but I'm going to also talk about the modulation. There were some ideas in the previous videos about the de-emphasis, decimation, and DC blocking, but I'm just going to go over them once more. So for FM modulation, what we need to do, we need to do integration of the signal we want to transmit and add that as the phase information of our signal. So what we are going to do is that, let's say our carrier frequency, which is our up mixing frequency, is 5.8 gigahertz. What happens is that in the baseband, we create another exponential form containing our phase, which is essentially a factor, which is the KF factor of our modulation, then integration of the data that we want to send. And then, so this is our baseband. And then after upmixing, this would be our whole data, right? That is going to be sent. So as we saw previously, in the FM demodulation, where we needed to do a derivative of the phase to obtain the signal. Now, in order to modulate using the FM modulation, we need to integrate it. One other thing I just added here, because we want to, in the future, go and investigate how to transmit and receive a stereo meaning that we transmit the data forward, left, and right speakers. Um, so that's why I'm just also adding with the data that I'm sending a 19 kilohertz tone as an indicator of stereo transmission. One thing to note here is that in this video, what we are going to do is that we are going to read an audio file which has an audio sampling rate, let's say 48 kilohertz. But if we want to send it to our digital to analog converter of, let's say, having a sample rate of 1 megahertz, what we need to do is that before sending it to the DAC, which is the digital to analog converter, we need to upsample 48 kilohertz signal to 1 megahertz. I'm going to show what essentially down and up sampling mean mathematically, but essentially what we are going to do is that we are going to add more data points to our data so that in a smaller time spans we have more information. the way that we do it is adding zeros uh, after each data to match to the sampling rate. So now that we talked about the FM modulation, I just want to show how we do it in the code, the actual Python code. I'm going to also, as the previous video where I shared the code for a spectrum analyzer in the GitHub, I'm going to also share this code in the GitHub so everyone can see and use it. Feel free to use it, and also please give me more comments and suggest me any feedback you have or any ideas for the future projects that come to your mind. So as I mentioned, I've downloaded a file. I've downloaded a copyright-free file because I wanted to play more, and as we are after we implement and we want to see the performance. So we just load the audio file, and the data and the sampling rate will be loaded here. Then what we are going to do is that using this resample poly, we are going to upsample our data to the TX sample rate. I talk about the mathematics behind the upsampling, but as I mentioned, it's just adding more information to the data to match the frequency of data to the sampling rate. Then this now we have the upsampled audio. Next step is that we create a time domain vector and also our pilot tone added, which is essentially a sign at the pilot frequency added to our data. Then we are creating the FM modulation by using a cumulative sum function, which is basically a discrete integration of the data here. And this essentially will give us um, the phase information. And the last step that we need to do is that create our baseband data by just putting this phase information as the power of our exponential. So E by power of our 1 J phase would be our baseband signal, right? Which is here. Then after uh, after mixer, where we mix it to FC, which is our carrier frequency, this would be the final form, A exponential of J 2 pi FCT plus 2 pi KF integral of M tau d tau. And FC here, we can choose any carrier frequency that we are interested in. For this video, I'm going to use 5 gigahertz ISM band, which is 5.8, because it's a band that we can use it for some amateur experiences. It's not being locked for other purposes. So that was the FM modulation. Now, FM demodulation, we went over this in the previous video where we talked about FM demodulation. But as I mentioned, I just brought the math we talked about in the previous video. But essentially, after we receive the data at the receiver and then down mix it by our carrier frequency, what you end up is the baseband, which is the same form that we had in here, which is exponential of 2 pi kf integral of m tau d tau, another writing of that here. And then what we need to do is that now that we have the phase information by just like saying and getting the angle of this, we get access to the phase information. And what we need to do is that we need to take derivative of this phase to find the actual data mt. Um, and one last thing is to wrap the phase, because usually once if the phase is wrapped, it may be from minus pi to plus pi, which basically this wrapping may hurt our demodulated signal because it may distort the data. And this way, we basically can transmit via FM modulation and receive it via FM demodulation. As you saw in this modulation, because we are putting all the information in the phase of the transmitted data, we are not considering or obtaining any information from the amplitude of the received data. And like before, I'm just showing how we implemented this in Python. We just, as I mentioned, we first normalize the received data to remove the amplitude information because we are just interested in the phase. Take the angle and then derivation and then unwrapping the phase. This would be our demodulated data. One last thing I just want to talk about is this resample poly is a very um, useful function that helps us to do up and down sampling. The implementation is a little more complicated. I'm going to in another separate video talk about the full math behind it, but I just essentially what it does is that it helps us to do the up sampling and down sampling that we want, because in our transmission, for our FM transmission, let's say we read the as I mentioned, we read the audio with 48 kilohertz and we want to send it uh, via a DAC that its sampling rate is 1 megahertz. So we upsample that 48 to 1 megahertz, then we send it, and in the receiver we need to do the opposite, meaning that once we demodulated the data, now the data is at 1 megahertz sampling rate. We need to downsample it back to 48 kilohertz before sending it to the speakers for the playback. What we use for those purposes, we use this resample poly function, and essentially upsampling means that we if we upsample by factor of L, we just after each data point we insert L minus 1 zeros after each data point. And the other uh, way is downsampling, which is we for if you want to downsample a signal, we need to do the opposite. We need to take every mth sample of the data to downsample the or decimate by factor of m. As I mentioned, we use this resample poly, which is a polyphase filtering. I'll go over the math behind it in a separate video because I don't want to lengthen this video. But this was a brief about the math and the way we implemented the FM modulation and demodulation. Now, let's go and see the actual Python implementation and run the code. Okay, now let's go over the code and see how some of these are implemented. As I mentioned, I'm going to upload the code entirely to the GitHub and put the link down below this video so you can see and download the code. Uh, so in the beginning, we are just defining some uh, variables such as RX sample rate, TX sample rate, or the audio sample rate that we want to read and write. Then we assign those to configure our SDR. Our RX SDR is at IP.1 here, and the RXLO is at 5.8 gigahertz. I set it here. This can change to other carrier frequency of interest. The same for the TX. Uh, I try to increase the TX buffer as much as possible because I want to transmit uh, as many as data possible uh, uh, to the to the TX buffer so that we don't ever the TX buffer never runs out of data. This is actually important because if you want to transmit and receive without any interruption, we need to make sure that there is a our TX buffer is always our TX buffer always has data to send, and there is no gap. Otherwise, there might be a scenario where the TX buffer runs out of data and nothing is there to send. So we will see a gap in the received playback audio. And to make sure actually this happens, I'll show later, I have put the TX data send, which is that just sending data to the TX buffer in a separate thread without any other processing in that thread to make sure that we always we always try to send data without any interruption or processing. Uh, this is like in the previous video that we created an FM demodulator. These are the uh, these are just uh, calculating the up factor, down factor, and also creating our FIR filter for anti-aliasing filter or the de-emphasis filter. We also have an audio low pass filter before sending the data to be played back. So these coefficients are calculated here. As well, we have a DC block filter because what happens is that because we are using a different transmitter and receiver, different ADALM Pluto for our transmitter and receiver, what happens is that if there is any frequency mismatch between them, meaning that the carrier frequency for each of them is slightly different, let's say 1 megahertz. Uh, what happens is that that information, that mismatch, will come as a DC information to our final demodulated data. Actually, we can use that to uh, identify the mismatch between the frequency mismatch between the transmitter and receiver and try to correct it. And this is what we are going to do in the next video when we want to correct the frequency mismatch between the transmitter and receiver. But even without it, because the FM modulation is more immune to this kind of mismatches, we can transmit and receive the audio with good quality. But these types of frequency mismatches are very destructive when we use higher modulations for higher speeds. For instance, QAM modulations in which all these frequency mismatches will cause rotation in the signal constellation and other artifacts. So here what we are going to do is that we just whatever DC information we have, because usually our signal shouldn't contain too much of DC information in it, our audio file. So I've added a DC block filter. But what we are going to see in the next video, where we are going to also correct the frequency mismatch between the transmitter and receiver, we are actually going to use that DC information to correct the mismatch. You will see that actually the amount of DC we see, the amplitude of the signal we see at DC uh, correlates very well with the delta F we have with the between the TX and RX. So because it's proportional to that delta F, we can use that information directly to estimate how much is the delta F, and we go and correct it using either creating an oscillator in Python in DSP or correcting it in by adjusting the RX LO frequency. But because at first I just wanted to go over the idea of FM modulation and demodulation, and we see the performance in one video, I just wanted to do that, and then we go and make the transmission better by removing all these imperfections. These are the threadings that I'm adding for different purposes. As I mentioned, to avoid any uh, uh, interruptions in the data, both at the transmitter and receiver, I'm reading and transmitting data in a separate thread. So there is no processing involved to slow down the thread that is uh, responsible to send and receive the data. These are some ideas about the pilot energy that I'm not going to over, but basically you can see this FM demodulation function here, that I mentioned in the beginning of the video, and this is the RX read thread where I read and apply all the necessary items, demodulations, the filtering before downsampling, then de-emphasizing and DC block, and then final low pass filter before sending the data for playback. The playback is in a separate thread. One last thing I just want also to mention, this is also the part that I mentioned in the beginning of the video where I'm just uh, modulating the FM data by just reading the audio file and upsampling it, taking the integration and then creating the baseband. And this is in a separate thread, which is called TX preparation thread, where I just do these and another thread, which is here, which is TX transmission thread, where I just in a separate thread transmit by TX.TX after like every time a separate chunk of the data. This way, I just make sure that that I'm assigning a separate thread to send the data to the TX buffer, uh, so I don't see any interruption in my trans. The rest are just creating some GUI for plotting because I'm plotting the final received spectrum here. And that's it. That's the implementation here. I'm going to run this code. First, after running the code, it may take a few seconds because the data, the audio file is being read and upsampled before it goes to transmission thread. So there is a few seconds of post processing involved. And after that, the transmission starts and we can receive the data without any interruption. I'm going to run the code and show you how it behaves. Okay, there you have it. Uh, there are some artifacts in the received data. Um, some of them are due to some of the filterings that are not very optimized, as well as if there are some gaps, like very tiny gaps, there is a chance that it's still like we may end up with a gap when transmitting the data. But it's interesting that we using ADALM Pluto and FM transmission, FM modulation, we can transmit and receive an audio file at a very high frequency of 5.8 GHz using a normal setup with not very expensive antennas that come with ADALM Pluto. Uh, I haven't tried how long how far if the TX and RX are from each other, we still can transmit with good quality. We will try that in the future, but but nonetheless, the results seem reasonable. One thing that is missing here is we need to do uh, frequency correction because we need to see basically how we can first detect the frequency mismatch between the transmitter and receiver and then try to correct it. There are uh, many ways that have been used and proposed to do that. For instance, frequency lock loops which using the received spectrum, either by examining the symmetry of the spectrum or other methods, we can detect actually the frequency mismatch between the transmitter and receiver. For this FM, actually, we can, as I mentioned, we can use the DC information to have um, a good estimation of the mismatch between the TX and RX, and we are going to first detect that and correct it. But because I didn't want to make this video long, I first thought to just have a separate video where we transmit and receive using FM modulation at very high frequency and see if we are capable of transmitting an audio with reasonably good quality, and then go and now make it perfect. Because as we learn how we can correct the frequency mismatch, we can utilize that as we move on to other modulations that this is much more those modulations that are much more sensitive to any frequency mismatch between the transmitter and the receiver. There you have it. I hope you enjoyed this video. Please share and subscribe to the channel. It's a very great support for me if you subscribe and also share this information with anyone that you think might be interested. And also, if you give me any comment or feedback on what you want to see, what do you think would be interesting to make, because in this channel we are going to see all these practical implementations of these interesting ideas, either high frequency communications in circuit implementation or using an SDR to make them. So please uh, support us, and I hope you enjoyed it once again, and thank you.